Hello, so my name is Bill Buchanan and I host a podcast on the world leaders in cryptography. And today I have a true world leader and someone whose research has inspired me for a long time. It's Anna Lysyanskaya. Have I pronounced that correctly?
Yes, very good.
It's not quite right, but I really appreciate you coming along for this the podcast. So Anna is a professor of computer science at Brown University. Her research spans many areas of advanced cryptography, including digital signatures, group signatures, blind signatures, eCash, and anonymous digital credentials. She was originally from the Ukraine and undertook her master's degree at MIT in 1999 and then went on to do a PhD in 2002 in the areas of signature schemes and applications to cryptographic protocol design. Quite a mouthful. She joined Brown University in 2002, as I said, and was made a full professor in 2013. She is a member of the board of directors at the IACR, along with serving on the scientific advisory board for the board of directors at the Electronic Privacy Information Centre, or EPIC. In 2024, she was awarded the Levchin Prize for a contribution entitled For the Development of Anonymous Credentials. So, what's your current role and what does a typical day involve for you?
I'm a professor at Brown. So a typical day would include a little bit of potentially teaching. So this semester I'm teaching a class called the Basics of Cryptographic Systems, which is a class that introduces students to what cryptography is, not necessarily computer science students or mathematics students. This is a class that is for a general academic audience. And the idea is that, in my opinion, cryptography is all around us. And if you want to make decisions about how to be a good citizen in the 21st century, uh, even if you don't need to understand the mathematics of cryptography, it's very useful to understand, for example, what encryption is, what's a cryptographic key, what's a digital signature, and what kinds of privacy preserving technologies we have at our disposal that might save us from the nightmare that's George Orwell's 1984.
That was the best selling that I've ever had for crypto. I completely agree, and I think our art, our science needs to be known about. The importance of every single connection that we make to the web is reliant on cryptography underneath for privacy and also for trust. So that's really excellent. So what were your school days like, your earlier days before university?
So I grew up in Kiev, Ukraine. So my childhood is like, so I'm sort of familiar with the Soviet life and then how the Soviet Union ended. And so my kind of intellectual tradition that I come from is a search for um, what it means to be an actual citizen rather than a subject of your society, of your environment, of your milieu. And that includes, of course, just understanding the basic concepts of what's a social contract and what are laws, what's the rule of law. Um, but also, of course, in the 21st century, it means what's the role that technology plays in a society. So at first, when I first went to university, I went to Smith College here in the United States in Massachusetts. And the attractive thing about going away to college in the United States and not staying in Ukraine for my education was the idea of liberal arts, which is also liberal arts and sciences, I should say, which is the idea that that the role of education is to create people who are thinkers, who contribute to society by having the intellectual tools to do so. And that includes the study of history, languages, but also mathematics and science. And that was extremely attractive to me as an idea. And that's that is why I applied to go to college in the United States. And then I ended up staying here ever since. And in college, in addition to, the more sort of liberal arts, I ended up majoring in computer science and mathematics. Even though I wasn't expecting to, I actually was very interested in history. I took a lot of classes in history and also biology for some reason, and French for some reason. I tried to branch out. But in the end, I decided to major in computer science and math, mostly because I felt that I was good at them. And so that I could make sort of the most interesting intellectual contribution by majoring in computer science and math. And that's what led me to cryptography, was the fact that it's just this perfect marriage of mathematics and computer science. And when I first started working in cryptography, I was not thinking about the broad societal implications at all. I thought of it more as a beautiful math puzzle. And then over time, I realized that actually it's more than that. Not just as an application, but also for me personally, it's more than just a beautiful math puzzle.
That's excellent. I'm the same. I read Bruce Snyer's book, Secret and Lies. He talked about public key encryption, and I was hooked with the beauty of it. And then I got into it and the Hellman method and so on, and I just got hooked. And every single day I read a new paper, and it's something new. It's endless learning for me. And so, what areas of research are you currently working on?
So the big theme of my research basically throughout my career is the thesis that whatever you want to do with data in a digital setting, you can do it in a way that respects privacy and that adheres to these data minimization principles, which means that you should not be revealing more data than a particular context strictly dictates. So, for example, anonymous credentials, the whole area of anonymous credentials, which is where I'm most active, is about the idea that when you want to gain access to some resource that requires credentials, so there's some kind of a verification step, a credential verification step, before you are let inside, that verification step does not actually need to learn anything about you except that you are an authorized individual, or maybe you're not an individual, an authorized machine, an authorized process. And that's all that it really needs to know before it lets you in. So more broadly, this principle of data minimization and privacy preserving cryptography means that in any particular context, if we respect privacy, if we feel that it's valuable, we need to kind of spell out what are the assurances that that are strictly required, and what data do we need to protect. And the minimization principle is that anything that's not strictly required needs to be protected, needs to be safe. So other problems with a similar flavor and similar techniques, for example, privacy-preserving electronic cash. So let's say that I want to send you a payment. The way that one would go about paying somebody on the internet today would be you either pay with your credit card, which means that you reveal your name, your credit card number, and there's also a third party to the transaction, which is the bank, who knows exactly what's happened. Or equivalently, you can pay by check in the United States. That's a very popular payment method. Or even worse, you can pay by something like Venmo, which makes your transactions public and readable to the whole world. But you don't need to, this doesn't have to be this way. There are privacy preserving e-cash mechanisms that would allow you to issue a token. So you withdraw money from your bank account and convert it into an untraceable token, which you then present for payment, which the recipient of the payment will be able to go to the bank and cash it in, and yet this token is formed in such a way that it does not have any traces of who it was who originally issued the payment. So this idea dates back to David Chaum in the 1980s, so this is known as Chaumian eCash. It's not as though anybody's actually using it, but any serious proposal for a central bank digital currency that is privacy preserving should incorporate some of these ideas, in my opinion, because otherwise we would have a banking system that is like the Big Brother in 1984, that is completely aware of everything that's going on at all times. And to kind of add to the story, so the plot thickens, one objection that one might say to this mode of untraceable electronic payments is that generally banking transactions, monetary transactions are subject to regulation. So one might wonder, if you have privacy preserving transactions, how can you regulate them? And so that's actually a very interesting question. This kind of philosophically sounds like, oh, maybe that's a paradox. But the truth is that regulation is in some sense orthogonal to privacy. You can do both. As long as we spell out exactly what is and isn't allowed, what is and isn't regulated, because then we can say, okay, you can have digital transactions where we preserve your privacy as long as you don't violate some constraint. So for example, if we're trying to protect an economy, I guess, yes, the economy from money laundering, then we would say, okay, you can have a privacy preserving digital payment as long as it's under a certain amount. So in the US, the money laundering laws, I believe, say that any transaction above $5,000 should not be in cash. Or even if it is in cash, the bank needs to report it when you deposit more than $5,000 at a time. So the way we would overcome this in this digital equivalent of cash is to say we design our payment tokens in such a way that if you are paying, if you are interacting with the same recipient and you give him more than $5,000 worth of your tokens, then the information in aggregate, that when you put all of them together, will actually tell us who you are. But if you don't violate that constraint, then you're privacy preserving. And the moment that we start thinking that way, they're like, okay, here are the constraints that as long as you don't violate them, you are your privacy is not violated either. The moment you go outside, don't use this mechanism, use another mechanism that would then record who you are. Or if you insist on using our mechanism, then we will just be able to trace you that way. So that's kind of broadly what I'm working on.
I think that's wonderful. I work on the academic advisory board for the Bank of England to look at the central bank digital currency. So the UK will hopefully have a digital pound sometime. And I keep saying again and again and again, the showstopper in this is the Bank of England's ledger. If that isn't anonymized, then it's a non-starter, and they're going to get into trouble. And you're right. I mean, the problem is this, that you have these regulations that need to be complied against. And I think one of the methods that was proposed is to have an escrow ID. So my accountant or something like that would keep my ID, so that if I was investigated, then they would
Right,
reveal who the identity was. But again, you're pinpointing them as part
right.
of it from that. The other one was the denial of service. Obviously, if it's free, then anybody could actually make a transaction and then bring the system down. So I think there's a lockdown period that might be proposed for that, so that you would only be able to make certain amount of transactions within a certain amount
Yeah.
of time.
Right. So exactly what you're describing are very specific constraints that we can meet with a privacy-preserving currency. And it would just be a technical requirement that is automatically followed, that no human oversight would be necessary past programming it a certain way. So it's very, very doable. And you can even do things like, I mean, this whole escrow of like having an accountant who could decrypt, who could find out whose transaction it is, that can be incorporated into the whole ecosystem so that you wouldn't need to involve the accountant specifically in every transaction. You simply encrypt your identity under some trusted public key, which potentially you can set up the system in such a way that the secret key doesn't sit in any one place, but is distributed, so that you would need a judge and yeah, you would need explicitly
A
the
warrant.
judicial
Yeah.
process to find out something about this transaction. And then you could attach this encrypted identifier to your transaction in a way that's verifiable, so that you couldn't fudge it, you couldn't attach somebody else's identifier. And then should an investigation be warranted, then we can trace what happened. So all of this it can be a component in a payment system. And many, many other, for example, we could say, okay, if you're under investigation currently, if there's a warrant to trace your activities, we can include that part in such a way that you wouldn't even know that you're being traced, but suddenly the transactions of individuals who are under investigation can be pinpointed. That's also possible. And everybody else's transactions would be private. So in my view, I'm very grateful. I should have mentioned it in the beginning of just after your introduction. I'm very grateful to be on your podcast because, in my view, one limiting factor, why aren't we using these technologies? I mean, one reason, of course, is that they're new. We didn't need them before, maybe because we were just fine with paper money. But another reason, I think, that we're not seeing wide adoption of these approaches is that they are complicated from the mathematical point of view and counterintuitive. And decision makers don't think that they need to invest the time into understanding them. And that in my view, that's an unnecessary limiting factor. And maybe as cryptographers, we can do something about it. We can educate decision makers better, not necessarily in like in a way that sort of tells them this is how you need to do your job, because I don't know how to do somebody else's job. I only know how to do my own job, but more as here are some tools that are at your disposal if you need them, and they're very cool and they're worth your time to try to understand. So I'm very, very happy to have the opportunity to talk about this with you today. And also, I'm very grateful that you're doing this podcast series in the first place, because I'm not the only cryptographer whose ideas I think are worthy of spotlighting.
Yeah. I mean, to me, it's a bit like a physicist meeting Albert Einstein. I get the chance to talk to people like you, Jan Kamenisch, Whitfield Diffie, Marty Hellman. I've read the whole history and the amazingness of it. So it's a privilege for me. And I think it's important. I think post-quantum cryptography is going to force the issue. I was in London yesterday. I talked to a whole lot of business leaders and say, you've got till 2030 before your public key methods, which is everything electronic on your system, is deprecated. And then by 2035, it's gone. So you need to be thinking now. And areas like homomorphic encryption with AI gives us the opportunity to really fix AI and the way it harvests personal identifiable information. So I think it's so important. But to go back to a point, so I think one of the most recent hacks, and I can't believe this happened, was bit by bit, 1.4 billion dollars was hacked, and it was a multi-sig wallet, and it was a cold store wallet, and so And guess what was the problem? It wasn't the crypto, it was the people, it was the social engineering.
Right.
So
Right.
obviously we are the problem. Humans are the problem. We implement things wrong. We are open to social engineering, and I don't think we'll ever defeat that problem. Do you think that's still a fundamental issue in this area?
Um, I think that we can do a lot about it. We probably can't eliminate it altogether, because, you know, people have been conned for forever. There's nothing there that can change human nature. I think that um, the really rapid adoption of cryptocurrencies um, is a phenomenon that I'm very surprised at that, because we have so many regulations for currencies, for regular currencies, that protect us from fraud. But in this space of cryptocurrencies, somehow the regulators have given up, or maybe they were too late to the party. I'm not sure what happened. Again, this is from the area of, I don't know how to do other people's jobs. I can't um, I cannot justify the use of cryptocurrencies at all. I think that they are altogether a scam from the very beginning. But again, this is what I've been saying ever since I found out cryptocurrencies are a thing, maybe 15 years ago, more than 15 years ago. Yeah, it's been a while. And I always thought this is ridiculous. From the point of view of the underlying algorithms, if you want a digital currency, even if it's like decentralized, distributed, so like even with these properties that are not true, for example, eCash. Um, I think that Bitcoin design and Ethereum's a little bit better, but especially Bitcoin is very clunky. Like, why it's not how I would have designed cryptocurrency. I think from the design point of view, something like Algorand or Dfinity is a much better approaches um, to a decentralized token. Um, but they're not the ones that anybody's using. But even if you have the best cryptocurrency design, the fact that there is nothing behind it, it's just a token, is still, in my view, an impediment to widespread adoption. Like, what does your token mean? Why is it valuable? And a lot of people would say, well, it's valuable because I buy it now at $1 a token, and tomorrow it's going to be worth more. And if that's your only justification, then it's just a scam. Then it's nothing. There's nothing there. It's just hot air. Um, if and for other people, the justification is that, well, it allows me to commit crimes. It allows me to pay in situations where conventional money isn't usable. So, I guess maybe we're getting a little bit off topic. Um, but the fact that money was stolen from these crypto wallets, well, yeah, not like, of course, money is going to be stolen from these crypto wallets. This design is not good enough. These technologies are not mature enough for widespread use. It's all a scam. Don't use it. That's my answer.
But the extension is really from cryptocurrency to crypto assets. So that's where we probably want to be, where we can actually create cryptographic tokens. I buy a car, I can have a cryptographically signed token and so on. And currently, legal people like to keep things nice and simple. They don't want to change all the rules and adopt cryptocurrency and crypto assets and so on. I think in Scots law, we're looking in this country to say there is property. So it'll be very simple for the legal system to say that this is now the same as a house or a car or something like that. And I think once we get that into law, some countries have a blockchain act, for example, that would actually define if someone was scammed, they would be able to get their money back. Companies need to be audited. And I think it's interesting. how we'll actually eventually have to adopt public key signing. In the EU, it's great to see that they're adopting this EID system, and with EIDAS 2, you'll now get legal certainty for signatures. So I think cryptocurrency has forced the issue because we had to move fast. The research is now in place, and now we can actually start to apply it to
Yeah,
real things.
that's
Perhaps that's the message.
I completely agree. That's actually the silver lining of the of this widespread um I, I guess glamorizing of cryptocurrencies is that it also means that people are now people have heard of digital signatures. Um, I I actually think that this EID, which is also which is a very exciting development, um, owes a lot not just to the fact that people have now heard of digital signatures um, from uh, the realm of cryptocurrencies, but there was one other step, which was the COVID passports. So the in my as far as I can tell, the European COVID passports was the first time that most people had a digital signature on their device that they actually understood what it was and how to use it. And maybe not everybody was, probably most people were not curious enough to actually try to understand how these COVID passports worked, other than, oh, there's an interface, I press a button, it shows my COVID passport to, I don't know, to the clerk who gets me in, who lets me go inside a store or something like that. Um, but it was the first example of um, a an identity credential that was ubiquitous. And now, because of the success of the adoption of these COVID passports, the EU is moving in the direction of let's just have a digital ID for other purposes as well, kind of a ubiquitous digital ID, um, so that you don't have to carry your any documentation on you. As long as you have a device and the device has this digital identity app on it, you're good. You can just show that. And of course, there are lots of benefits because even if you lose your device can be replaced. It's easier to replace than to deal with sending you a new passport, reissuing paper credentials. So that way, your paper credentials, even if you have them, you can just safely keep them at home in a safe place, and you will be less likely to lose them. But it introduces a host of new problems, and one of them is going back to what I mentioned earlier, the Big Brother in 1984. Now, if every time you go somewhere, you are showing this government issued digital credential, does that mean that now the government can know everything about you, all of your comings and goings, and have like not just know it kind of as a like a general, I have a general sense that probably at this time of the day you're going to be in your office. So okay, that's fine, that's a guess, but has a verifiable digital trail of your comings and goings. So not only do I think you're in your office right now just because it's a weekday afternoon for you, but I know it for sure because you've digitally signed something with your digital ID that you carry with you all the time. So it becomes an issue. So to address this, the European Union, which has very strict privacy laws, and it really means them, people really care about their privacy, also stipulated that this digital ID needs to be privacy preserving, as in when you show it, let's say you show it twice, those two different showings cannot be linked to each other. Even if there's collusion between everybody to whom you're showing your credentials, they cannot figure out that it's the same person. And to take it one step further, even the issuing organization should not be able to trace that it was you. Like, even though they're the ones who issued you these credentials, they should not be able to tell that it's you. So that's that was in the law that they wrote, that they adopted, that kind of jump-started work on these digital IDs. And I think it's an interesting story because they started working on how to do this kind of, they just used the COVID identity app, the COVID credential app, as a starting point and tried to extend it to other forms of credentials. And then they said, look, we can do this. And to make it hard to link, maybe we just issue credentials that can only be used once. Then they showed their designs to the public and invited comments. And specifically, they welcomed comments from cryptographers. So so some of us were invited to come and well, virtually attend a presentation that they gave on their designs. And all of the cryptographers on those calls got together and said, wait a minute, this is not this is not how we really want to do digital ID, because even though the motivation, we like the motivation, we agree with the principles that you're trying to implement, but we think that the algorithms that you're using to implement them are not good enough. They're not meeting the specification you've given for this. So we wrote a little response to these designs, and it's still ongoing, and we're still optimistic that the end result will be a digital identity app that actually is privacy preserving, that adheres to the principles that I mentioned earlier. And I just
I think
realized,
that's excellent.
yeah,
Yeah, yeah.
I didn't
Go
address
ahead.
your comments about the post-quantum cryptography. That's of course
Yeah.
very, very important. So it is true that the horizon. So who, first of all, let me just address very quickly who sets these rules. Like, why do we have until 2035 to move to post-quantum? It's not just because there are efforts to build a quantum computer, which would mean that very wide the algorithms that are very widespread right now, such as the Diffie-Hellman key exchange algorithm or the RSA trapdoor permutation, the quantum computer can break them. And we are watching as physicists and engineers are building these quantum computers. They have not been able to break encryption yet, but they make progress, and it is a possibility that they will be able to do it 10 years from now, maybe not 10 years from now, maybe 20, 30, maybe even 50 years from now. But because it's a distinct possibility, we need to transition sooner rather than later. And so NIST, the National Institute of Standards here in the US, issued this guidance. I think for now it was just a draft, but they're finalizing it to spur the transition. And if you read that, what they published, the intention is for the algorithms that are in use right now for things like encryption and authentication, and sorry, I should say encryption and digital signatures, like digital certificates. We now already have post-quantum analogs that can be used. And in fact, some companies, some vendors have started using them. For example, Apple gave a talk at, I guess not Apple itself, but Frederick Jacobs, who works for Apple, gave a talk at last year's Real World Cryptography Conference, announcing how Apple is using post-quantum algorithms for authentication right now to move to the world that's post-quantum secure. So it's completely realistic to transition that infrastructure into post-quantum analogs. And NIST is therefore saying, look, if you want to do business with the US federal government, you need, by 2035, you need to use those existing established post-quantum analogs. That's what we expect. But to kind of look at the fuller picture, not everything has a stable post-quantum analog yet. So for example, for anonymous credentials, we're still working on it. It isn't fair to say that we know exactly how to do them in a way that's post-quantum. So in the meantime, it would still be a good idea to use the ones that we have that are not post-quantum. It's better to use those, at least for the time being, in my opinion, than to just give up and say, oh, well, since we don't have a post-quantum anonymous credential, we're just not going to use anonymous credentials at all. It's fine that that would enable total surveillance by government. It's not fine. Let's use the best that we have, which right now, in my opinion, is kind of more old school anonymous credentials that require the kinds of building blocks that a quantum computer would unfortunately be able to break. So it's in the long term, we have to transition away from them. But for now, perhaps we can live with them. That's my my kind of big picture take on where we are with post-quantum
You,
anonymous credentials.
yeah, you've opened up so many areas, and I need to reply to a few of them. You're completely correct with the COVID passport. That to me was the shining light. It's the first time I could actually see it working, how we could move across borders, how we could set up a public key infrastructure that wasn't necessarily PKI, how we could have a ledger for public key trusting, how we could remove that if there wasn't any trust. And I think that was a shining light. It just hasn't happened at scale after it. It happened in the NHS in the UK. You could see that people were moving towards that, but I still don't have a healthcare record in the UK at all. I don't do digital signing. I don't have a wallet for healthcare. We do see the signs of it in the UK with the driving license that will be. I know that you have that in the US just now, but what an advancement! Yesterday, I didn't take a bit of paper with me when I flew to London. Everything was on my phone, all my flight details. If I'd lost my phone, then I'd be stuck in London somewhere. But I trust the whole infrastructure now, and we need to start to digitize. So I'm completely correct. The thing that happened in the UK in 2001, we nearly had a digital ID system, but one anonymous blog post killed it flat because it said the government wants to spy on you. Don't do it. Don't believe them. And that's the situation that the EU or any country in the EU is going to be faced. That if it's seen that it's one ID, you've lost it. If you think that you're going to merge all your IDs into one place, like your Gmail address and so on, that will lose it. But I think the other thing is obviously that tracking issue. And then to come on to your last point, you brought up so many things there. So Lattice is the new kid in town. I've talked to quite a few Lattice people, Chris Piker and so on, and they talk about some of the primitives are there. Like Shamir, we just love Shamir. We love Shamir shares, and there is now that distributed signing that's possible. But you're right, the bilinear pairing and all the other magical things aren't quite there yet, but I'm sure they will happen. But you're right, our toolbox hasn't been renewed with Lattice, and all these methods still are relevant. So it brings me on to 2001. I know that was a while ago. 2001 was when NIST approved the AES standard, and 2001 was when the digital ID system was dropped in the UK. So you and Jan Kamenisch wrote a paper on the efficient system for non-transferable anonymous credentials with optional anonymity revocation. Can you remember what the core contribution of that paper was and how it's been used in future work?
So that was the paper where we showed that you can have credentials that are issued to you in a way that is that privacy preserving, that minimizes the data that you disclose about yourself. So, perhaps you've earned some kind of a customer credit somewhere, or some senior discount or whatever it is that you've earned via your relationship with an organization. The organization doesn't need to know anything else about you. It's ready to issue you a credential, and it can issue your credential in such a way that it really is issued to your device, it's tied to your secret key, just like a credential issued by any other organization will be tied to the same device, to the same secret key. And none of these organizations can link you to together. Like they each you have a relationship with each of them using a different pseudonym, and they cannot tell that it's the same person. And yet you can show your credentials to different organizations, also in a way that is unlinkable, so that they can see that, for example, you have a credential from, I don't know, NHS or something like that, but they don't know who you are. And even if they join forces with the NHS, they could not link and figure out which NHS citizen, patient. So that's what. Oh, and we also had so we had a way of doing it that was efficient enough that it could be implemented. And in fact, Jan then proceeded with jointly with Els van Herwingen to implement this design. So he then wrote another paper, which I thought, well, maybe that's not implemented yet. I thought it's a good idea to keep working on the theory. So I was like, maybe it's too soon to implement. So I didn't end up part of that project. But Jan said, no, it would be fun to implement just to see what it looks like. So he then proceeded to implement it. And then I thought, oh, okay, well, actually, maybe it was worth it to implement just to show that, in fact, it is practical. So then Jan and I continued working on like in that area more and more and more, and we refined our ideas. So we kind of distilled what it actually means, and we realized that all it is a digital signature with protocols. So then that was the version that I wrote in my PhD thesis, because I was trying to adapt this contribution to kind of long form thesis form. And I realized, oh, this is the best way to think about it, is not as just, oh, this is a credential system. No, it's easier to think of it as there's a building block, and it's actually a signature that has interesting properties. And then anonymous credentials are an application of this signature. So that was our paper that appeared in SCN 2002. And then we thought, oh, wait a minute, like our original idea was from the strong RSA assumption, but in 2001, but what's a long time ago, but bilinear pairings were all the rage. So it was new and shiny and amazing. And we thought, oh, wait a minute, you can do it from bilinear pairings. So then we just kept having more ideas. I mean, the whole time we thought, oh, like, let's maybe we should write a journal version of our original paper. But instead of writing journal versions of our paper, we just kept writing new papers.
Yeah, and I think bilinear pairings have been such magic in the area and have helped so much. So can you explain, I know this is a really difficult, I wouldn't want to explain to the general public what a bilinear pairing, bilinear mapping was. Do you have an easy explanation for that?
I don't know if it's an easy explanation. I can try to explain it.
Yeah.
I don't know if I would say that it's an explanation for the general public,
Yeah.
but it's an explanation for people who are already familiar with the Diffie-Hellman key exchange.
Yeah.
So if you remember, if you know off the top of your head how the Diffie-Hellman key exchange works, we have two participants. We have Alice and we have Bob. And before they even start exchanging anything, they've already agreed on using a particular algebraic group for this protocol. So they already have an algebraic group with a generator G. Let's call it G. And they also know that this group is of order Q, as in there are Q distinct elements of this group, and Q is quite large. So if you just draw an element from the group at random, it can be one of Q distinct elements, And we assume, this is the discrete logarithm assumption that comes from the original Diffie-Hellman paper, we assume that it's hard to figure out. You draw a random element, let's call this element A, and there is some alpha such that this, if you take the generator G and you raise it to the power alpha, you get this A, but it's very hard to find this alpha. So that's the discrete logarithm assumption. Anyway, this Diffie-Hellman key exchange goes like this. Alice picks a random A. Actually, let's say she picks a random alpha, and Bob picks a random beta, and both of them come at random. It's an integer between 1 and q. And then each of them raises the generator G to the power that they've picked. So Alice comes up with A, which is G to the alpha, and Bob comes up with B, which is G to the beta. And then they send those values to each other. And of course, that's kind of the basis of, for example, TLS. TLS also has a step where not only do they send them to each other, they also digitally sign them so they know that they come from the right place. But
Even
never.
the middle, yeah.
Okay, so that's so that now they've exchanged this. Now Alice received from Bob his B, and she can raise it to her alpha. So now they get G to alpha times, she gets G to alpha times beta. And Bob can do something similar. He received A from Alice, and now he can raise it to G. Sorry, he can raise her A to his beta. So now he gets G to alpha beta. So now they have a value that nobody else can compute except for them, because they have these. So Alice has her secret alpha and Bob has his secret beta. Okay, so that's just Diffie-Hellman key exchange. Where do the bilinear pairings come in? So the bilinear pairings comes in. This is from one of the early cryptography papers that use bilinear pairings by Antoine Joux, called tripartite key exchange. Bilinear pairings comes in because now suppose that we have a third participant, Charlie, and now the three of them want to have a key. So in classical Diffie-Hellman, what can Charlie's role be? There's nothing for Charlie to do. So Alice can compute G to alpha beta. Bob can compute G to alpha beta. Charlie, he sees A and B flowing by, but there's nothing for him to compute that the three of them would share. A bilinear pairing gives Charlie the ability to do that, because a bilinear pairing is a way to say, to take two group elements, A and B, and map them to some element of a third group in such a way that you can still exponentiate in that group as well. So now let's say that Charlie has a secret gamma, and just like Alice and Bob, he takes G to the gamma, and that's his C, and he sends that to Alice and Bob, and he also receives Alice's A and Bob's B. All right, so now the three of them together can compute a shared key. How do they do that? Well, what Alice can do is she can take Bob's B and Charlie's C. She uses this bilinear pairing to map them to this third group. And this pairing has the property that once you pair it, it's like you're taking the exponents and multiplying them. So now by just pairing them, so far she hasn't even used her secret yet. She just paired them up. And now she gets some generator of this third group. Let's call it H. So she gets this H raised to Bob's beta and Charlie's gamma. So it's H to beta gamma. And now she can raise that to her alpha, and she gets H to alpha beta gamma. So now she has this key that is derived from all of their exponents, all of their secrets. And Bob can do similarly. He can pair up Alice's A and Charlie's C to get H to alpha gamma, and then he raises it to beta. So this is what a bilinear pairing is. It allows us to kind of move to yet another group and multiply just once, multiply something in the exponents. So it's just, it expands our toolkit of the kinds of things we can do. So that was all the rage back in 2000, 2001. It also enabled Bonnet and Franklin's original identity-based encryption scheme, which was a big deal. And it turns out that in this setting, we can do more interesting things. So for example, in that setting, we could design a signature scheme that that lends itself more easily to being able to the design of anonymous credentials. So I don't know if that answers your question.
That's fantastic. That was a really excellent explanation. I'll try and draw this along with the YouTube video and to show the tripartite key exchange method. And you brought up a few things there. So you talk about Q. Q is obviously the prime number that you use. That's mod Q. And I think an important thing is you brought up the order. I don't know what you would define that as. I define that as N, and it's really important. And a discrete log, then it's the order is Q minus one is the total number of mappings that you can have. But an elliptic curve, then you can't have all the points. I think it's when I realized with elliptic curve cryptography, it wasn't that lovely analog thing, that it was all just little dots on the screen. There was two dots for every X value.
Yeah.
Like in a square root, you've got a plus and a minus. I thought this is just wonderful overall. So I think the order is so important. Not so much for discrete logs, but for elliptic curves, the order gives you the security level. Basically,
Right.
that's the number of possible points that you get. Do you work in? You obviously work in elliptic curve
Yeah.
cryptography a lot.
Yes, I do, but I have to tell you, I work in a like I try to abstract it away. For me, in my work, I find it a lot easier to not actually think about the underlying structure of the group and to just think of it very, very abstractly. Um, and sometimes it's helpful and sometimes it's a mistake. So if you don't look at the underlying structure of a group, if you just say I have a group and it has these properties, that frees you up in some sense. It frees you up from thinking about unnecessary details, and then you can kind of be, at least I can be more creative if I don't think about the structure of the group. But then the downside of that is, of course, that an abstraction is not always a perfect reflection of reality. So then it's important to kind of bring it back to the original, like what do I need from this group? And if you follow the work on bilinear pairings, the evolution of papers on bilinear pairings, and this is like me kind of looking at a little bit of a side seat to this. Like I did not develop any of this, in my opinion, very beautiful and fundamental cryptographic machinery. When bilinear pairings were first introduced, we thought that there was the kind of the group of the domain, like, and then there's the target group, and we kind of thought of them as just two groups. There's just the original group from which things come before you apply the pairing, and then there's the target group. And that abstraction was, very nice. It allowed us to do something interesting. But it doesn't quite capture the underlying mathematics, the elliptic curves. So because the pairing itself, the algorithm to pair elements, does not treat its two inputs equally, like they're not actually the same group. They're kind of, first you map something to something, just so then there was a revision of what's actually happening under the hood. And the revision was that actually there are two different groups. So, three different groups. So before you apply the map. So in other words, if we go back to our tripartite picture, what's happening is that they need to, well, actually in a tripartite picture, it's convenient to think of everybody's using the same generator of the group and raises it to their exponents. But that doesn't capture the situation where the two groups, when you that you're pairing, are not the same group. So if you start capturing it, then we have a different abstraction, and this is now what most current papers that use bilinear pairings will use the so-called type 3 bilinear pairings that explicitly think of these origin groups, domain groups, as distinct groups. Not only are they distinct, even though both of them are of order Q, there isn't, you might be able to map, there isn't a mapping between them. And this kind of more refined abstraction of bilinear pairings allows us to actually enrich the class of things that can be done with them. Because now, if there is no mapping between those two original groups that we're aware of, like then it's sort of valid to say, well, let's assume that there's no mapping, that we cannot efficiently compute an isomorphism between them. And that means that now we have another class of computational assumptions that are realistic, and that buys us more interesting things. So for example, if you make this assumption, then we can have more efficient something called structure preserving signatures, which is also a building block for anonymous credentials, and Groth-Zakai proofs, and a whole host of other things become realistic and realizable, and there are implementations and libraries that even do that. So anyway, all of this to say that I like it when there's just an abstraction, because then I don't have to think about the low-level details. But then if I lose track of the low-level details, then somebody else comes up with this beautiful beautiful idea that there are these type 3 pairings that are much more useful. So anyways, maybe it was a little bit of an aside.
Yeah, no, that's really interesting. And I think that for any PhD student who's really listening, I think that's really important, is to abstract that detail away, and it's up to someone who can implement on the different methods into lattice or elliptic curve. But I think when you see some of the really great people in cryptography, they do abstract that away, and they're thinking this is a Schnorr problem and this is a Diffie-Hellman problem, and I'm doing it with lattices, but it's still the same old method that we're using from the 1970s. I like that type of approach to it. And it's when you trace the area back, you go back to the 1960s with the Lucifer cipher through IBM. IBM was it still is a big player in this area, and I know that Jan worked for IBM Research in Zurich, I think it was. But then it was 1976 and 1977 that the Big Bang happened, and we're still feeling the remnants of that Big Bang overall. So we had Diffie-Hellman. It's amazing when you think that Whitfield Diffie thought the idea up of public key encryption, but it was Marty Hellman who did the discrete log, just as you were talking about. The two of them worked together very well in working through this paper that combined the two of them. But then the Big Bang happened in 1977, which was reversed. Shamir and Edelman created this amazing RSA method. It's still the most popular signature method on the internet just now. That's nearly 15 years, 50 years, 5 decades. And you worked at MIT around that 2001 time, and I think you worked with Ron. What was it like? What was it like to be in that environment? It must, because you've got Stanford and you've got MIT. They're different.
Not Stanford, yeah. But, well, okay, sorry. Continue. Go ahead.
Yeah. So I just wondered what it was like. I mean, you've obviously been influenced by being in that hothouse of amazing people. Maybe you just saw them for one talk. You've got Gobwasser and I mean, there's so many great people. When you speak to the great cryptographers now, the professors, and they say, I went to one talk from this person and that inspired me to do this. What was it like being there at that time?
So I arrived at MIT in 97. So the master's that I got was kind of on the way to PhD. So it's a one integrated program. So in 1997, Ron had just finished a little bit of an interlude in machine learning theory. So if you had a similar podcast series on machine learning, you might get, somebody who was also Ron's student, like Avrim Blum, for example, was his student in that machine learning period. Um, and you might ask him the same question: what was it like to work with the great Ron Rivest? So Ron left an enormous made enormous contributions, and not just in cryptography, but much more broadly than that. Anyway, so he was just he had just kind of decided that he wanted to go back to working in cryptography and take a break from machine learning. And we had, so at MIT, when I first showed up, I wasn't actually sure what I wanted to do. I had all kinds of ideas, but I was very attracted to theory because of it's a blend of mathematics and computer science. So I went to kind of an orientation of the theory of computation group had an annual corn fest where, you know, we get a bunch of corn, we shuck it, we boil it, we eat it, and we all introduce each other. So Ron introduced himself and he said, oh, and actually I just, you know, I'm restarting work in cryptography again, and I'm looking for new students. And I thought, oh my God, that's amazing. Like that's I can't believe it. I'm so lucky. So then I immediately said, oh, if you're looking for new students, can I work with you? You know, what can I do with you? And so what Ron did was said, sure. And he gave me a paper to read. That paper was Kamenisch and Stadler's group signatures from Crypto 97. That was actually, that became the basis of Jan's PhD thesis. So Ron gave it to me to read and say, why don't you read it and present it in a crypto seminar? So then I did that. And then I had a friend who also was like the same reaction to Ron's spiel, like, wow, I want to be Ron's student, Zuli Ramzan. So Zuli went to Ron and Ron gave him a paper to read on blind signatures. So then, like a week later, having read those papers, Zuli and I are talking to each other and we're like, oh, what's a group signature? What's a blind signature? Let's see if we so that's how I wrote my first paper. Is Zuli and I were like, oh, let's combine these ideas together. So we were both very, very excited at this opportunity. So then that's how I first started working with Ron. And then a little while later, a few months after that, he gave me another paper to read, and that one was on what later we started calling anonymous credentials. Anonymous credentials, you know, didn't quite exist the way that we've defined them later. But Ron was very interested in this. So he's the one who kind of who introduced me to these ideas, and with whom I kind of my thinking, the way I think about cryptography is very much due to to Ron's influence in my life.
Yeah, that's great. I did invite him to come on the podcast, and he said he's busy with other things that aren't academic and outside of academia, and I think he's enjoying his retirement or semi-retirement just now. I hope he will come on because that would be such an honor. I think to speak to him and Audie Shamir would be definitely like speaking to Einstein if you're a physicist. So he's done such great work and he's continued it. I mean, I think there are some great people who can do a great pinpoint of research and then everybody else follows and they lose it. But there are some people who continue to find new things in new areas. And it's almost like their mind is working. And the three of them worked so well as a team together. Ron was the thinker, the trier out. Audie Shamir was the cracker, and Len was the formal mathematician. And those three skills really niched together very well. But it was great that you worked in that team. It's obviously influenced you, and you can put it on your CV. I worked with Ron Rivest. That would be an amazing thing on your CV. So explain group signatures. I know they've been used in we use them. We've actually written a paper recently about how we could use them with EID. To keep this anonymization. I know they've been used in cryptocurrency and so on. Could you just explain what a group signature is?
Yes. So in a regular signature, you have a public key that is associated with you, and then and only you know the corresponding secret key, and then you sign on behalf. You can think of it as you're signing on behalf of this public key, and everybody can see your digital signature and say, aha, I know exactly who signed it. That was Bill because it's signed under Bill's public key. In a group signature, the public key is associated not just with one individual or device, but with a group of devices or individuals. And each of them each device or individual has a distinct identity, potentially also that corresponds to some public key, but the signing key is associated with the whole group. And when you issue a signature, it can be verified under the group public key, and everybody can see, aha, this is a signature from, I don't know, what's a good affiliation for you? Edinburgh Napier University. So this is a signature from somebody affiliated with Edinburgh Napier. And the important key, the important property of a group signature is that it hides the identity of the signer. So we can see that it's a signature from somebody from Edinburgh Napier, but we cannot tell who specifically. So if that were the only property, that would be really trivial to realize such a signature, because then you can just say, well, here's a public key, here's a signing key, here's its corresponding secret key. Let's give the secret key to everybody from Edinburgh Napier. Now they can all sign under this key. So that would be trivial if that were the only property. But it's not the only property. The other important property is that to every signature, there's a ground truth. There's a particular signer who actually issued it. And this signer can be determined. There is a way to discover the identity of the signer if you know an additional tracing key. So this is a tracing key that's like, you're supposed to only use it in case of emergencies. So under normal circumstances, let's say that I come and visit you in Edinburgh Napier. I would love to, by the way. I looked it up. It's in a wonderful neighborhood of Edinburgh that
Yeah, it's lovely.
Anyway, so I get an invitation. Anybody can verify that it comes from somebody in Edinburgh Napier. That's all they need to know. They don't need to know specifically who invited me, just to kind of let me, I don't know, get a visa or whatever it is that I need, whatever kind of paperwork I need to come and visit. But should something go wrong, like maybe I'm doing something I'm not supposed to, and now they need to investigate who was it that invited you, then there's a process where they go and discover the identity of the signer, and they discover that it was you. And it's important that they should not be able to blame you for inviting me if it wasn't you. So that's a group signature. And it's, of course, a very attractive way to do digital authorization for many scenarios, because we don't want to leave traces about like the internals of an organization. We want to protect, like, how does the organization make decisions about who to invite, who to authorize. That's proprietary information. It's none of anybody's business. But at the same time, if something goes wrong, we want to be able to understand what went wrong and have a mechanism to trace it. And just like other related technologies, so it's related to anonymous credentials, right? Because the idea is that you can demonstrate that you're authorized. Like you can digitally sign on behalf of a group. So that's kind of a demonstration that you are in that group, that you're authorized to speak on behalf of this group, and you're not revealing who you are as you do this. So it's actually, it's extremely related to anonymous credentials. And in fact, you can combine it with anonymous credentials. So you can think of anonymous credentials as like a generalization of group signatures, and you can think of group signatures as a special case of anonymous credentials.
That's great. Because I know that I think it's either Monero or Zcash that use it, that tries to bring together the public keys of entities that have the same spending as you. I don't know quite how they do that, but obviously you would see a spike in someone who, I don't know, bought Porsche cars or something like that. So they try to bring the group together to be the same so that you can't actually pinpoint which one. And I think it was Ron Rivest, I may be wrong in this, who was the first person to propose this as a whistleblower in the White House. I think that was the original paper. That might be from 78. I mean, he must have had such a peak intellectual rising at that time, because the three of them, Shamir too, obviously did the Shamir shares that are still around. And you've published work on adaptable threshold signature schemes. Can you tell us what those are? And I think one of your paper talks about erasers.
Uh-huh.
Can you explain what an eraser might be in
Sure.
that?
Erasure. So, okay. So these are all variations of a signature scheme. So in the threshold signature scheme, you don't have just one participant, one person who has the secret key and the ability to sign on behalf of this key. Signing is a process. It's kind of, you need to have a critical mass of people deciding that they all want to sign and they all contribute to a signature. And then from their contributions, you can assemble a signature. So that's a threshold signature. If a threshold in this phrase refers to, you need to be, the number of signers needs to be above a certain threshold before a signature can be issued. So this is attractive when you want the signature to mean more than just, oh, this device authorized this transaction or stands behind this, but when you want to say this organization does it. So it's not just one particular device, but a whole slew of them. And it minimizes a single point of failure. So you mentioned Shamir secret shares. So that's in the same vein as a secret sharing protocol would say, well, even if one machine is hacked or lost, we still have others. So as long as the number of failures is below threshold, we should be able to reconstruct the secret and recover from it. So it's the same with the signature. Like even if some small number of participants falls prey to an adversary, as long as it's below threshold, they cannot do any damage. Okay, so now where do the erasures come in? So it's a little bit of a technical point, but it's important if we're thinking of an adversary who's malicious and very resourceful, and it corrupts a device, and once your computer is corrupted, the adversary can examine its memory and see what's happening and what's happened. And so obviously, if you have a secret key stored on your device, the adversary can easily just read it, and now the adversary is in possession of this key. But the question is, what happens if you had a key in the past and now you've erased it? You think you're done with it, and you've moved on. And so you think, well, I don't have anything on my device that's sensitive because whatever I had is no longer relevant. So then you sort of, in order to securely erase a key, you need to make sure that it's really erased, really wiped from memory. So then we need to think about, how does computer memory actually work? Can you actually erase? And the truth is that it's kind of annoying because it depends on what you want. You can't do anything. If you don't want your memory to be easily erased, like if you want to stop yourself from glitches, you probably can't really do it because they're like issues. And so you need to back up your data because you might lose it if you don't back it up. But on the other hand, if what you want to do is erase, you also cannot safely erase. Why can't you safely erase? Because your data is not just in one place. It's going to be in your disk. It's going to be in your cache. It's going to be in your active memory. It's going to be on your backup drive somewhere in the basement. So it's very hard to erase. So it's hard to keep your data, and it's also hard to erase your data. So you can't win. So the good news, however, is that if we design our cryptographic protocols such that they don't require people to erase data and still maintain security even when there are no erasures, then we can mitigate the problem that it's hard to erase. So that's what that paper was about. That was a while ago. So we showed in that paper, we showed the two protocols for threshold signatures, I think it was threshold signatures.
Yeah.
And one
Adaptive. Yeah.
yes,
Yeah.
one protocol was much simpler because it directed participants to erase some data when it was no longer relevant. And the other one was much more complex because it didn't. So that's what that was about.
It's great, yeah. So I know there's things like the Feldman secret shares and Peterson secret shares where you, if you find out that one of your shares has been corrupted, you can regenerate, you can kick that share off the
Right.
network.
Yes.
So you,
Yeah.
you never
That's
have a dealer,
yeah.
and that's the
Yeah.
problem with any secret share system, that the dealer has all the cards. So I think something like the Feldman system, the private key never exists
Yeah.
anywhere, but they can all
Yes.
negotiate. But what happens if one of them is taken over? I think with these methods, you can actually recompute and kick that one off the
Right.
network.
Right. But then because you've now done this, so now you made your old shares useless.
Yeah,
So that's good.
yeah,
But you we still want to make sure that your old shares are like no longer vulnerable. So
yeah,
like, right. So that's kind of the problem, is that if you want to refresh, regenerate, there's a whole area. It's called proactive cryptography, which which means that as time passes, even if you're not like, even if chances are very low that you're going to be broken into today, but if we look
yeah,
at a bigger time window, like over the space of a year, 5 years, maybe you will be hacked at some point during the 5 years. So we want to kind of refresh your keys so that, if the hacker breaks into your server today and into my server tomorrow, the snapshot they get from you is not even compatible with the snapshot they get from me, so they cannot reconstruct it. Like it's not like over time they accumulate everybody's secret share and then can reconstruct the secret. We keep refreshing the shares, but that also requires that we be able to erase them. Otherwise, the whole exercise is pointless. Um,
yeah.
yeah, so erasure is
What,
very
what we yeah, what we want is a Mission Impossible type scenario where this message will self-destruct after 1 minute. We've never really solved that problem. Maybe trusted execution environments and secure
yeah.
enclaves might be able to do that, but in a world of AI agents and so on, you've got to really worry that there might be these AI agents looking for keys and so on. So you worked with Jan Kamenisch. What was it about working with him that made the both of you such a great research team?
Um, so that's a good question. I think that our biggest advantage as a team is that we're very different from each other.
Mm. It's a good
So
thing in
he's very
research.
tall and I'm very short.
I didn't think of that, yeah, but yeah, from a
Uh,
research point of view, you're
yeah,
different. Yeah.
he's very, calm and even keeled, and I'm very incredible. And also the way we think is kind of complementary.
Yeah.
So there's just something magical. But when you have a collaborator where just being together in the same space brings the best out of you, it's very hard to explain what it is really. Um, but it's just that when we're together, um, we just bounce ideas off of each other, and we end up with some new ideas that we're both really excited about. So I don't know if I've answered your question, but it's there's
Yeah, no, I
yeah,
think that's
yeah,
exactly, and all of the great teams that I've
yeah,
talked to, it's typically that they are
yeah.
different people. They have different skills, like the Reves, Shamian and Edelman. They did things differently, and the team worked together. And without the third person or the second person, it wouldn't have worked overall. So, if there's one thing, this is always a really difficult thing to ask. If there's one thing in your career that you would have changed, would you have stayed at MIT? Would you have not went to MIT? I know that you have a perfect career and you're in a beautiful university and everything has went well for you. But if there's one little thing that you would have changed in your career, what would it have been?
That's a good question. I don't know if there would have been one thing that I would have changed in terms of what I did. I think as I got older, and especially now that I have kids, um, I kind of feel that I need to be more patient. And I
Mm.
especially needed to be more patient when I was younger. To just kind of have this sort of confidence to pause and think and let things play out. I feel that that's a super strength that some people possess, and I only strive to possess it. So that's probably what I would have tried to change about my thinking and decision making, is try to imbue it with a little bit more patience. In terms of kind of my career trajectory, yeah, I agree with what you said. I feel like I'm very happy with all the choices that I've made. I am extremely fortunate that I was able to go to Smith College for my undergraduate degree. I I'm a little bit sad that I haven't been back in Ukraine recently, especially, given current events. And I'm almost in daily contact with my friends and loved ones there. Um, and I feel like maybe I could have given back a little bit more to Ukraine. So that's not so much about my career. It's more kind of how I feel. Um, but I'm very happy with my with going to Smith for my education and not staying in Ukraine. I'm very happy with going to MIT. And I'm also very happy with the fact that when I went there, that was maybe a very unique moment in my life, in that so many things were open to me. Like, I could have chosen a completely different field. I could have worked in AI. I could have worked in computer systems, but I chose cryptography. Um, and I'm so lucky. I feel like this was the best choice for me. No question about it. I'm very fortunate that I ended up making the connection with Jan that I did. That was also actually completely by chance, because in '99, I had already spent 6 years in the US, studying in the US. And I thought, oh, I kind of want to travel. And maybe I can go to IBM Zurich, because I know people there. They have, the good cryptographers, but also because it's right in the middle of Europe, and then I can just
Beautiful.
see more of the world. It's like I kind of had this. That was how I picked Zurich. I wish
Oh,
I
you
could say,
actually
oh,
went. You went
yeah,
there.
yep,
You did go there just to see Europe and
yep.
Switzerland.
And I wish I could say I picked it because I wanted
Yeah.
to work with Jan, but the truth is that I actually started at IBM Zurich before Jan. Jan didn't
Ah,
arrive until like a month and a half into my internship at IBM
all
Zurich.
right.
Um,
Okay.
so anyway, but the fact that like I had this chance, and I I was kind of open to it. And so there's this comedian, John Cleese, who of course is a British
Yeah.
comedian.
Yeah. Yeah.
So
Went to my film.
he has this video about creativity that I love. I keep watching it over and over again. And in this video, he talks about something he calls closed mode and something he calls open mode. When you're in open mode, um, you don't set you that's really the definition. You don't close yourself off to possibilities. You kind of say, oh, here's an idea, and here's another idea, and here's like all these cool things, and I'm going to be open to all of them. Whatever ideas flow, whatever connections I make, it's just like, it's all, the more the merrier. And I'm not going to limit myself. I'm really going to go um after any exciting thought. I'm going to try to pursue it. And I'm not going to be rushed out of this open mode. I'm not going to let a deadline interfere with it. I'm just going to say, well, it's like, whatever you want from me 5 minutes from now is not like, that's not as important as letting my open mode flow. And then there's this closed mode, which is when actually now I really have to produce like something. I have to put it on paper. And I really I love that idea. And I really feel like there are stretches of time that you owe it to yourself. And when I say you, I mean everybody. Like, any individual must allow themselves these stretches of open mode, when you just don't let things get in your way. Don't think that, like, oh, I have a deadline, I have to turn in something tomorrow, so I have to like focus on that now. Well, yeah, you probably should, focus on this at some point, but that's not so important. What's important is to not close yourself off to things. So yeah, that's
I agree, I agree. And it's like being a child. Like, why is the sky blue? It's funny that I was in the car there and I heard the tick, when you turn a corner, you get the ticking of the indicators, tick, 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 tick. And I was trying to remember at the time when I bought a car and I had to replace one, and it was a little piece of metal inside that heats up and does click, 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 click.
oh,
And obviously they don't use that. I don't think so these days. Uh, and they obviously replicate that in an electronic way, so that you hear the click, click, click. And obviously we don't question these things. Where does this click, click, click sound? And I'm sure around the world it's the same click, click, click that you get everywhere. And I think as a researcher, we need to think, we need to ask questions, the simple things. And it's like a child does this. A child, you say, that's a silly question. And it isn't a silly question. Why is the sky blue? Has an answer. So I think your approach to really spending time thinking, spending time reading is really important overall. Can I just go back to the IBM side again? Because I've interviewed quite a few people from IBM, especially the work on post-quantum cryptography and the lattice work that they're doing just now. And it seems that IBM does have a real core interest in groundbreaking research without necessarily knowing that it's going to lead to some profit in the end. What was the ethos of IBM? Why was it so successful in this field?
so I don't know if I'm necessarily the right person to answer it because I was just there as a visitor,
Mm,
and like summer student for a couple summers, and then a visitor later. Um, so I think it's probably a question to people who spent more time there to understand the internals. But from my perspective as a visitor, I thought it was, especially IBM Zurich, um, it was because people were not stressed. At IBM Zurich, you there's this wonderful cafeteria that I've never had a cafeteria like that anywhere else where I've worked. Where you come to work, and then at around 10 in the morning, everybody says, "Hey, let's go have coffee." So you go, and you think it's social time, but it's not, because you get your snapshot into what everybody's doing, what everybody's thinking, what are the cool new developments in everybody's field. And it's in a way that's very unstressful. So you have people of, amazing caliber, like very, very brilliant people who are together in the same space and not very stressed, just having coffee together. And then everybody has lunch together. And then everybody has more coffee in the afternoon together. And it feels like all we're doing is socializing. But then we go back to our offices and we, continue kind of working on whatever it is we were working on. And it's sort of a nice mix. It's nice, unhurried, like and relaxed. So that's kind of how my time there was. Of course, as a visitor, I was shielded from the nitty gritty, like where does the money come from for all this, right? Somebody has to pay for all of
yeah,
this. I mean, we pay for the coffee, but
yeah, yeah, yeah.
so I think that um, it's probably values, and also IBM Zurich is different from
Mm,
other branches of IBM
mm,
in that it's eligible for government funding in Europe, uh, which means that it's a good place for these very large contracts that require um, both cutting edge research, but also like implementation efforts, like to make something real. So I think they've been very successful in attracting research money, um, which of course the Europeans are making a very big very substantial investment in research. And I think that kind of as a society, we've gotten sort of complacent. We're like, yeah, research happens and we're taking it for granted. But it requires, decades of investment
yeah,
to maintain the edge, to maintain competitiveness. And government funding is key, like as society is investing. And if you look at kind of the value for the dollar, it's incredible. Um,
yeah.
and so I think that those are probably the key ingredients.
Yeah. Yeah, I completely agree. I think it was once explained to me by a researcher in IBM. It's like academia, but perfect. So you don't have all that having to teach students and all the admin. You know how you have to do 25% admin as a professor or something like that. You don't have to do that. I thought that was a brilliant explanation. If you love research and R&D, then industry research is almost like the perfect form of it. Academia is going to be tainted because we've got to teach students. Well, we love teaching students, of course, but obviously that brings a little bit of admin. But then we've got to be a program manager or we've got to do some administration that we don't like doing. It's funny that Niall Kobolitz is a really interesting, the co-creator of elliptic curve code, a really interesting person completely. And he talks about having to do admin, and I don't know, he's the director of programs or something. You say, what the the person who invented elliptic curve cryptography is having to do admin? What's going on here?
So I wouldn't complain too much about academia,
Mm,
actually. I mean, I really love my job at Brown. I get to do the research that I feel is important. I get to spend the bulk of my time on it. I get to do it with amazing PhD students who I'm learning from all the time. So I'm not entirely complaining. And also, actually, I guess you asked me in the beginning, and I didn't complete my answer. You asked like what's my day like. So other than teaching, so recently I was elected as a vice chair of what we call at Brown the Faculty Executive Committee, but it's basically faculty governance. So it's
yeah,
my job, and next year I'm going to be chair. So this is kind of the nature of this appointment, which means that my job next year is going to be to represent all of Brown faculty, all of the professors at Brown, to the Brown administration. So
wow,
I'm actually so
a big
that's
job.
it's a big job and there's a
The
lot of
professoriate. Yeah,
admin
yeah,
component to
yeah,
it, but I don't actually think of it that way. I kind of think that this is my chance to learn about what else is happening at Brown and what are my colleagues doing and what what is this enterprise that we call education, academia, university? What is it all about? And I think it's extremely fundamental to the human species that we maintain our curiosity
yeah,
and our investment in intellectual development. Um, and that also that translates into new and better technology. It translates into um, a better lifestyle for everybody and more happiness, hopefully, in the world.
yeah,
So I think actually I disagree that a research lab is the perfect place. I think universities are okay.
yeah. Yeah, they're good. I mean, when you think about it, to be a teacher and a mentor is probably the best job that anybody can have. To have a student will, if they graduate, they'll either punch you in the nose when they meet you later, say you did this and I didn't like it, or they'll shake your hand. That's a unique thing that one lecture, that one thing that you actually said at that time inspired someone. It's like a small little thing, but for someone, it's the change of their career. And I think it's a unique opportunity. And obviously, PhD students are as much a mentoring process, them growing, them being a novice apprentice at the start, and at the end, they're getting there, but then to see them blossom over the years is something just like your children, really. It happens with them. So I feel like this is just part one of our discussions. And I think I've scratched the surface on your research and your viewpoints on life. And so I'll end on a big question, and that's if you were a new researcher now, what problem would you address?
In cryptography, I think
Oh, and anything. I mean, if you were given, and you talked about history, you talked about going to Zurich. I know that you came to Edinburgh, so you've obviously know the planets, you know lots of things. So just say that everything reset and you started a new career, a new research area. What would it be?
so. I mean, it depends because not everybody is like me. So not everybody
Mhm.
has the same taste as me. Uh, Given my like if we're talking about somebody who is like me in that they really love mathematics and they love the power of abstraction and proof, um, and but they're also very interested in things that have applications, um, then I think theoretical computer science is an amazing area to get started with. And I view cryptography as a subfield of theoretical computer
Yeah,
science.
yeah,
Uh, and then I think cryptography has a lot of open problems that are extremely important. I mean, you mentioned post-quantum cryptography. That's, of course, a very fast-growing field, very mathematical, very intricate. It is actually, in order to contribute to it, there are a lot of papers you need to read. You need to read first. So it's a fantastic for somebody who's just starting out, it's a good thing to start with. Um, because when you're at the beginning, you have to read a lot of papers anyway. So those would be the papers that I would be reading now is Chris Spiker's papers, for example.
yeah,
Uh, I guess I am reading them.
yeah. They're
um,
brilliant. They're really
yeah,
great. In one
right.
paper, you'll learn everything about the field. He doesn't have any fluff. Some research papers you read now as a reviewer, well, that was 20 pages of just filler. Just give me what it is. But with Chris, the whole paper is the fundament. It's like a book. It's like a book that's been condensed down to 30 pages. Really brilliant work.
Yep. But cryptography is not the only field. There are exciting things happening in algorithms as well and complexity theory. Um, there kind of things at the intersection. Those are always very interesting things at the intersection of, say, machine learning and cryptography. Um, and there are many things. So, for example, there's the part of, you're trying to learn from your data, but what if some of your data is provided by an adversary? So this corrupted. So that's a really hard problem. And the more experimental machine learning researchers, that's not something they encounter experimentally, right? You really have to think like a theorist. You have to think worst case. You have to have a theorem that says, even if the adversary corrupts a certain fraction of the data, I'm still learning something meaningful from it.
Yeah,
So yeah, so those, I mean, I I I don't know where I would land today if I were just starting out. It's
yeah,
possible that it wouldn't be
yeah,
cryptography, but also I think it's quite possible that it would be.
yeah. And you talk about adversarial because obviously in this area you've got to think like Eve and Mallory.
Yeah.
You've got to think of the adversary. And that's what I love about cryptography is that it's not just you, but you've got to think of the other person who's smarter than you, who has more resources than you. And it's amazing that academia and academic research gets to a consensus to say this is correct. And it's good that NIST have adopted a lot of the methods that we've used in academia to make sure that the standards that they create are peer reviewed and that the NSA, even though they might try, don't have an influence in the final choices. But who knows? You don't quite know what's happened with these things. But hopefully we
They
get to
tried
some
once.
consensus. Yeah.
So they tried once.
Yeah, they
NIST,
did. Yeah.
NIST suffered a huge reputational damage as a
Mm.
result of even letting NSA in the room,
Yeah.
and they're not going to make that mistake again. So I
Yeah.
think they'll it's
That's right. That was the elliptic curve
yeah.
random number generator. I think it was found by someone in Microsoft, as I remember. That was really quite embarrassing for them. So hopefully that won't happen again, and hopefully the S boxes and symmetric key are okay, and they don't know how to reverse them, and all our public key methods are secure. Well, thank you so much. This has been a real privilege, and I really do think this is just part one. I think we could probably talk for another 10 hours about, I mean, I just scratched the surface. We didn't even get up to 2002, which is really quite bad. So I really think there's another chat that we can have that takes us from 2002 to where you are now. But it's been a real privilege, and I hope, and I've taken so much of your time, which I apologize for. But have a great rest of your day, and keep up the great work. Really, such interesting work. Okay, thank you.
Thanks for having me on. It was a real treat.
Good. Okay.